All right. So welcome everyone to join the monthly development meeting. And then this week we're continuing our work for the Phasic policy gradient. So let me get started by maybe start sharing my screen. Has anyone taken another look at Phasic policy gradient or experimented with it? Any thoughts before I show any further things?
I did some experiments, but you might as well go ahead.
Okay. Well, I really don't have a lot of updates. This week I was basically trying to run the PPG just on the CPU side, so it actually works. So I guess the good thing is that we can kind of confirm that PPG has higher sample efficiency according to this chart right here. However, I have to sort of terminate this experiment today. This has been going on for 5 days. I had to stop it because for my job, there's something that I install and I need to restart, which is kind of unusual for Linux, but I had to do it, and that's the reason I had to stop it. And I didn't save the model, so it just kind of hangs around here without ever finishing it. So because of its memory requirements, it's just a really big issue. I think maybe something for the next week I can try is to run PPG with just smaller batch sizes. Therefore, I might be able to use a GPU, which may make the experiments a little faster. But yeah, any thoughts, guys?
So could you maybe walk us again
Um,
at the step where the GPU memory explodes?
Yeah. I don't know if I mentioned this last time, but basically, if you're training the agents using PPG on this ProcGen domain, you're storing a lot of stuff in the ProcGen environment. So what happens is that let me maybe download the log files. Okay, it's not really available to download. But basically, you go to 500,000 time steps. I actually did this calculation in the Phasic policy gradient official repository as well. Let's take a look, because other people are having issues with the CPU requirements, and I was basically just replying something real quick. So this is their pseudocode, right? And then here initialize the empty buffer. And MPI by default is set to be 32 by 34, MPI is set to be 32. And then the end steps, which is how many environment steps each environment will take by default, the parameter is 256, and you have 64 environments. So in total, you're looking at 500,000 instances of observation of this shape, 364, 64. And these observations will be stored in the buffer. And so which means the game will run for 500,000 time steps before this auxiliary phase even kicks in. And then once this auxiliary phase kicks in, they split this buffer into 16 pieces. So which is this hyperparameter number of mini batches per epochs per MPI. If you split them up, then it's 30,000-ish observations in the aux phase. And then essentially you're looking at this, which is just you're creating a bunch of arrays, 30,000 of them, and each of them is 3 by 64 by 64.
I will say it's not just the data itself, but the resulting operation, the gradients.
Yes, absolutely.
Yes, understandable.
Yeah, so when you do the neural network calculation, right, it's more than just this observation is part of the picture. When you pass those variables along, there's a lot of intermediate calculations, right? So maybe I can pull it up real quick.
So maybe instead of the hyperparameter number of mini batches, how about using the size of the mini batch itself and divide it all the 500,000 time steps accordingly?
Give me 1 second.
But it's probably gonna take quite some time.
Yeah. Okay. Here. Procgen visuals. Just want to show you a quick thing. Right. So, for example, when you eventually when you have this, however many, 30,000 observations, you pass it into this actor, and then you get this variable, which is also 30,000, and then you're passing it to a categorical 30,000. Basically, a lot of variables they really stack up, and that's when the memory sort of blows up.
Understood.
Yeah, so Rosalind, are you suggesting that maybe we can have a smaller buffer?
Not necessarily a smaller buffer, because I actually think it plays a really important part in the algorithm. I think in the text just below the algorithm, like 1/16, it's like number of mini batches per auxiliary epoch.
Yes.
So they're trying to end all the updates using 16 batches. So I would say, since we have limited GPU resources, we would instead have to do many more batches of smaller size, basically.
Yeah, I think that's a very reasonable thing to try. So for us, if we try 32 or even 64 mini batches, that's probably going to work better for us.
Maybe 32 or 64 as the size of the mini batch, not the number.
Sure. But so the current implementation, right, for PPO, even for the batch for the policy, you just sort of specify the 16 number, and then they divide the entire data sets by the 6. It's just easier to tune. Like if you choose 64, you have to sort of make sure that they multiply up to the entire number. In other words, if you just specify, how many mini batches you want, it's a little easier to control it.
Okay.
Yeah, but either way, we can tune it to 6. The mini batch size, we can tune it down to 64. Yeah. So that
something in the lines of 256 should probably be more manageable.
Yeah. That's going to be that's going to be for sure be very manageable.
You will have the n dimension of each action will be 2048 basically.
Yeah.
Instead of 32,000.
Yeah. So I think Phasic policy gradient, at least according to the experiment results that I have right now. Also, by the way, if you look at the PPG results right now and compare it to the paper's results, what you'll find is that our performance doesn't exactly match. So, for example, in this environment that we're experimenting in,
Star Pilot.
Yeah. What appears to be the case is that at 50 million time steps, in Star Pilot, PPG is already reaching about 18, but that is not the case with us. We're reaching about 5. So I have a couple theory for why this is the case. The first is in the original PPG implementation, they're using a larger neural network. They're using the sort of Impala style neural network. I think. Sorry, what?
They will have probably a better representation, which helps generalize across the.
Yeah, exactly. So our neural network design is a little bit more arbitrary. So that might be, I would imagine that's the main reason. Everything else, there's some very minor differences. Like for example, the policy scaling, the bias on the last layer of the policy initialization in PPO in OpenAI baseline's PPO implementation. I think it was 0.01 for the policy. But I think Phasic policy gradient, they use something like 0.1. But those are, I don't know, it just feels so minor. It shouldn't impact the performance. But other than that, well, obviously our PPO implementation is also underperforming than what has been reported in both the PPG paper and the project and original paper. Again, I suspect it was because of the neural network choice. Instead of using Impala sort of neural network architecture, we're using this kind of just a AtariNet, very simple neural network architecture. Yeah. Any thoughts?
I'm not really familiar with Impala. Is the architecture there even more memory consumptive, or is it?
Yes.
Is it pretty? Okay.
So if you go to Impala paper, basically they're a little larger and they have some different neural network types, but that's not going to be that's in my opinion, that's not going to cause the memory to blow up. What causes the memory blow up is the 30,000 observation size. So over here, you have the small Impala model, which is similar to what we have, except ours doesn't have the LSTM. So with LSTM is 1.2 million parameters, and the large is 1.6 million parameters. So I guess without LSTM, it'll be 1.6 divided by 1.2 more parameters. It'll be 14% more parameters, which is kind of nothing. Another thing that I want to okay, this is kind of scrolling up for some reason. Just kind of forgot what I was gonna say. But yeah, right. I was going to calculate this. So over here we have this, right? What if we get their product? This is 400 million numbers, or so if you're using the Impala model, you have 1.6 million parameters, but over here you have 400 million. They're not really parameters, so you don't have a gradient for them, but they're 400 million sort of elements that you're passing into the neural network. So for me, they're the ones that are causing the memory explosion rather than having a large neural network itself.
So if you lower that size, I would lower this, but it probably make the gradient steps a bit more noisy. So would you need to add some further regularization in order to control for that?
Are you saying add some noise to the observation?
I'm not sure what kind of regulation would work best here, but yeah, maybe some noise or maybe some clipping.
Mm-hmm. Yeah, I think that might be interesting research directions. If you add some noise, especially for the project environment, you're looking at this pixel-based inputs, and maybe if you do some, like you mentioned, if you do some sort of noise, it may help the agent to generalize better, right?
Oh yeah, it's data augmentation.
Mm-hmm. Yeah, for sure. Other than that, I don't really have too much update on the Phasic policy gradient. It just really takes a long time to run, and for the most part, I'm just kind of waiting for the runs to finish. Anyway, another thing that I've been kind of looking at is faster policy gradient algorithms, or just faster reinforcement learning algorithms in general. One thing that I noticed is that a lot of even the more popular reinforcement learning algorithms, like DQN or PPO, they're not really using the GPU that well. So if you look at the system paths of our experiments, wait a minute. This is PPG. The PPG one doesn't use GPU. So if you look at the PPO one, the PPO uses GPU, but what you'll find is that the GPU utilization stays around 5%. Which means when you're really using GPU to do things...
5 points.
Huh?
Utilization, okay.
Yeah. So you allocate a lot of memory. So over here, because we store the observations and actions on the GPU, so GPU uses a lot of memory. But in terms of GPU utilization, I don't know how it is calculated, but the name seems pretty intuitive. It means we're not doing GPU calculation that often. And then if you're considering some of the more distributed work that we've done, like for example in one of the Apex environments, Apex algorithm, where we basically have a worker and we have multiple workers and multiple actors and just one learner, and the learner is always doing GPU updates. If you take a look at its system usage, what you'll find is a much higher GPU utilization percentage, which is around 30%. Still not 80 or 100%, but it's a much higher GPU utilization. And when you compare the wall time, basically the higher GPU utilization, the faster your algorithm is going to be. So
Apex wasn't.
You
were just referring to Apex, right? Using four more times GPU.
Yes, has a much higher GPU utilization. Like if you see over here, this is kind of a reward graph, and what you find is Apex reaches 350 rewards, and in comparison, if you're just using DQN, it takes about 25 hours, but using Apex, it finishes within 4 hours, and if you use PPO, it finishes in almost 6 hours. So it's even faster than PPO, but PPO really should be faster if we were to implement it in a similar manner. Yeah, I don't know. If people are interested, I could also talk a little bit about how Apex works.
Wait, I saw you had some PPG results for breakout, for example.
Yes. That was kind of just a preliminary try. Now that I understand it more, I probably set the parameters for the PPG Atari not correctly, which is probably why it's performing so poorly. It runs both slower and achieves worse results. But probably because of the auxiliary phase. I was trying to use a GPU, so I make the auxiliary phase much more often, I guess.
And it ran for 10 million timestamps.
Yes. Yeah, that's also a drastic difference as well. Let me see its hyperparameters. So what is this MPI?
MPI is probably the number of times you update the policy.
Yes, so I used 16 as the aux phase, as the MPI, so which makes it twice as frequent to do the auxiliary updates. And also, just in general, the hyperparameter is very different for the for Atari and the Procgen. So I don't know, what is the best way to account for the discrepancies. Yeah, any thoughts? I'm sort of, out of things to talk about for the PPG, other than just to say, next week I'm going to try maybe a smaller batch size and see how it works. But
I guess I could chip in just a little bit.
Yeah, absolutely. Go ahead.
On my, let's say, improved understanding of the algorithm.
Okay.
Well, as I am a lazy person, what is? Okay, yes.
Yes, we can see your
Well,
screen.
I first tried experiments on Atari environments since it was easier to just repurpose the already existing, I think, PPO Atari.
Yes.
Right.
Mm-hmm.
So, well, it seems to work on at least the breakout and bonk. Here, the PPG is in the orange color.
Mm-hmm.
Not really pretty, but there is some learning happening.
Could you sort of smooth the curve a little bit?
How much smoothing do you want?
maybe sort of like a 0.9.
Wow, that's a lot.
Yeah. Okay. Did you use the reward calculation correctly? Because it looks like the performance varies a lot. Are you taking into account of the only recording the episode reward after all 5 lives are finished?
I am not so sure about that. That
Can you-
will depend on.
Can you show me the source code?
Yes, in a second. Actually, there is quite a few more elements.
Yeah. Please show first, and then we can get back to it.
It's not PPG exactly yet.
Okay.
Where is the charts? Maybe are you talking about the episode live?
Yeah. Then yeah. I just saw that you're implementing it correctly. Yeah. So since you didn't modify that part of the source code, you should be fine. So if you go to not over here, but go down in the policy rollout section of the source code.
It's somewhere. Rollout is here.
Yeah, so if you see episode in info.keys, so that's because we're using the episode, we're using a gem wrapper to record the episodic statistics. So if you're using that to log the episode reward, you should be fine. However, show me your the other thing. Show me your make env function. Show how your envs are constructed.
Makem's is actually pretty much unchanged.
Yeah. Then you're doing it correctly. Then it's a little bit surprising to me how your performance is much more unstable. Just kind of
Well, as I said before, it's not actually PPG yet because I noticed the auxiliary updates are not done over enough data.
Okay.
But this was just kind of a sanity check, I guess.
Mm-hmm.
And well, the orange, there is a blue line if you notice.
Yes.
The blue line is actually just simple PPO.
Okay.
Without the auxiliary updates. But just by adding one auxiliary update phase, there is already some performance improvement. So I thought it as a kind of demonstrates the validity of the PPG, right?
I don't quite understand, but PPO is able to reach about 400 episodic reward. Why does it show?
Okay. One more difference on that blue PPO is that the value network and the policy network are not sharing anything.
Okay,
So maybe that's why. It's not exactly the original PPO either.
I see. I see. I almost feel like there's something, maybe a bug, because your PPG implementation or the blue line is just so unstable, and then if you look at the breakout runs in the benchmark, they're more stable as you learn more.
Yes.
Yeah, I don't really know why. I can take a look later too.
Now it's probably the separating the networks that caused it.
Okay. Okay.
Otherwise, it's the same PPO at a recall.
Okay. I see.
So, what I realized just this morning, is that I did not exactly do the phase iteration, nor the phase, nor the iteration. If you recall, in the original PPO, yes, you have like for updating.
Mm-hmm.
The focus is still on the, how do you say that? The update steps, right?
Mm-hmm.
You sample for a number of steps and then you do the updates over here using all the data collected.
Mm-hmm.
So what I actually did was, on top of the standard, let me see. Yes, the standard PPO updates. The difference is that there is the value network is separate now.
Okay.
And we add just a single auxiliary update here, using the small amount of data that was collected in the same rollout.
Oh, okay. I see. I think that's probably why it caused the performance to degrade, because the aux phase really should happen, after a lot of policy updates. So you're basically
not only a lot of policy updates, but over a lot more data.
Yeah, so you're basically doing this with npi equal to 1, I think.
1, exactly.
Yeah.
So that's why I said it's not really PPG yet.
I see.
Which made me think that actually this initialize empty buffer and here, those two steps are probably more important than they look. And they actually take that PPG takes PPO closer to off-policy algorithm, I would say, like DQN.
You mean PPG is more similar to off-policy?
Well, maybe not similar, but it borrows the data reuse aspect.
I think the aux phase definitely is very off-policy.
Off-space? Apex? Which algorithm? Okay, the auxiliary phase. Understood.
Yeah.
So I was also thinking, like here, we are computing the VTarg
in
one iteration, then adding it to the buffer. But at the next iteration, since the VTarg uses the updated value function to be computed, I was wondering if there would be a kind of discrepancy in the data in the buffer here. As the V is updated, the VTarg should be quite more high variance, I would say, intuitive.
Yeah, that's interesting.
Basically, what is the VTarg? VTarg, they say here, it's computed using...
So, the VTarg is based... Yeah, is... So, how you calculate the VTarg?
It's probably B returns.
Yeah, it's basically the B returns. And the B returns is calculated after you calculate the advantage. And You use the but basically it's not just a vanilla return, but you have some sort of you're using the advantage to plus the values. But the advantages is calculated using GAE.
So it's actually independent of the value function? Maybe only when we bootstrap. Okay. I see. So it makes sense. Here I thought at this step, the change in the value function itself would somehow introduce some noise in the data. But since it's mostly independent of the value itself, because it's using GAE, so it's actually quite a uniform data sample.
Oh, I see. Oh, that's a good point.
But still, when doing bootstrapping, we are calling the value function, so maybe there is a little bit of interference, but probably nothing important.
Yeah, those things are, I would say, probably should ignore it or whatnot.
Yes. So since the core feature of the PPG, the auxiliary updates, seems to work somehow, I guess this week I will be properly implementing the phase iteration kind of training loop and take into account your observation on the batch size of the auxiliary updates to be able to run them on GPU.
Yeah, I think that's reasonable. We should just try to run some experiments. I'll try to run some experiments to maybe sort of wrap up. I'll try to at least in the Atari domain. Maybe let me try with different mini batch hyperparameter, and maybe if I can show that PVG is more sample efficient, we'll be sort of done with the monthly development cycle, because I don't think it's practical to it's just very expensive to run these experiments. It's not 10 million. Yeah.
Okay. One more thing I wanted to check with you was the usage of the clip vloss, because I think it is enabled by default.
Yes, so that is also a difference. So over in Phasic policy gradients implementation, they didn't use clip loss for the PPO.
They did not use it.
Yeah, they did not. I also don't think they use linear learning rate annealing as well.
Is that one also enabled by default?
For PPO, yes. For me, for PPG, I didn't enable it, which may be one of the reasons why it's performing better.
Is putting it to false actually enough?
Yes.
I believe.
Yes. You feel free to print it out, but yes, I think so. Here, let me just show you an example. Over here, I have the PPG example running somewhere. So my PPG's implementation, I disable it. So if you go to its hyperparameters and go to linear rates, annealing maybe. What is the parameters name?
It's anneal _LR, I think.
Yeah, so did you see that?
There's a search bar in the...
Yeah.
Yes, okay.
Yeah, so if you just put it to false, you're good.
Okay.
Well, which is the reason why you use the sort of a Boolean flag that way in all of the scripts that we have. Yeah.
Well, that's pretty much all I got to do on PPG this week.
Yeah, great work. I'm very glad that you got it working for Pun, but it appears in Breakout it's a little bit unstable.
Yes. So the sample efficiency, maybe compared to the original PPO, it might be good, but could you please bring back where you got Apex and all those guys?
Yeah, so here is how you can find it. If you just go to the benchmark, and then over here you have the Atari, and here have metrics, logs, videos recorded at, and you can just click on the Atari reports. Or you can just go over here, just click on the reports, and you can find Atari. And then at the very end is the breakout example. Yeah, I think you should try to do a file difference between my PBG Atari implementation versus yours. Maybe we can find out something, because mine doesn't have the instability that's kind of shown on your
How much
experiments.
smoothing? Oh, well, maybe if there is no smoothing, the curves are indeed more centered.
Yeah. I didn't, even if a lot of smoothing is used, I don't think it's as unstable. So if I'm not using any smoothing, right, then it looks like this. But it looks a lot different, I guess.
Yeah, that's actually why I don't really use smoothing. It's like,
I
give me
see.
the raw truth. Is it learning or not? Kind of.
Right. Yeah, it makes sense. Yeah, so I don't know.
Do you have some Pong?
No, I just run it with breakout.
Okay, no worries.
Mm-hmm. But yeah, that's kind of what I have. Any thoughts, guys? Anything you want to see?
I guess no experiments yet with varying npi or epi, number of times the policy is reused. I know they showed that one was the best, but just wondering if
Yeah.
it's been replicated.
So they're basically saying you should not reuse a policy. So if you have a higher epi, what they show is that the performance decrease as you increase the policy reuse. So you really should be using the policy the same way as you did for A3C.
Corey, I was wondering if that's an experiment that it's worth trying again. But it looks pretty universal in these environments that they show in the paper, at least for those 16 of them.
Mm-hmm. Yeah.
And it's gonna be expensive.
Yeah, it's very expensive. For me with CPU it runs 10 days. That's just too much. But by the way, for the NPI, they're basically showing you. So NPI 32 means you're gonna run the policy rollouts for 32 times before doing an auxiliary updates, which means you're gonna run the game for 500,000 time steps before doing a single auxiliary updates. And then to 16 means, I guess, you go to 250,000 time steps, then you do auxiliary updates. To 8 means 125,000, and then you're going to do auxiliary updates. So basically, the smaller the MPI, the more frequent you're going to do the aux updates. And what they show is you should have a really high MPI. But yeah.
Wait a second. The NPI, following your explanation just before, it seems that the NPI actually influence the amount of data that will be leveraged in the
Yes.
auxiliary phase, right?
Yes.
Because although we have many NPIs, we still have the ePi and EV hyperparameters that control the policy updates themselves.
Mm-hmm.
So NPI is probably more about the data
Yes.
that is provided to the auxiliary phase.
Exactly, yeah. So higher the MPI, the larger the B is going to be.
Oh. Data reuse, indeed.
Yeah, which I thought was pretty interesting. Why don't they just put an MPI equal to 64? But
Now you know.
Yeah, now I know. Now I know. But yeah, any other thoughts? Or we can sort of end our meeting a little earlier today.
I'm good.
Okay. Well, sounds good. We're going to sort of end our meeting today a little earlier. Thanks everyone for coming. Next week we're going to try to wrap this up. Just maybe run a few more experiments, and yeah, that'll be all. Thanks everyone for joining this meeting today.
Thanks, folks. Have a good weekend.
Thanks. Yeah, have a good weekend.
You too.
All right, I'll see you guys.